As a Python programmer, I, like many others, use Matplotlib for basic data visualization. Visualization was always an extension to the core of my particular Python programming, compared to visualization first, code second people. Those are the animation artists, graphics engineers, etc. They work with software that is way more capable than Matplotlib, like Blender, Unity, or OpenGL. So here's the niche for this video. You use Python, and you've probably used Matplotlib for some visualizations, and now you want to try some animation without switching from your favorite IDE and without needing to learn Blender, Unity, etc. And you're wondering, should I use Matplotlib and its animation library for this, or should I try something else like Pygame? Because you suspect that Matplotlib has its limits. I considered trying Manim as well, but I got this prejudice about it that it's too mathy. PyQt was another option, but it became Matplotlib Animations versus Pygame. So basically, I animated the exact same thing in them many times with various settings to compare them. Here's an overview of the topics that will be covered. What will be shown? A solar system. So these planets and moons are PNG images stored in this folder here, and then they are moved, rotated, and modified in Matplotlib or Pygame. This type of PNG animation is called motion graphics or image panning, and that is an important caveat or delimitation of this video because this is admittedly pretty far away from Matplotlib Animation's core use case. Basically, the core use case looks something like this. Take some data points and plot them through time. But I needed image panning for this project, so if you're looking at doing an animation that includes the movement of cropped images, this video is for you, but if you only want to plot dots like this, it's less relevant. That having been said, this animation also includes dots, as you can see. They are depicting rockets that fly between the planets, and I was thinking about including experiments where I remove the PNGs and only show these dot rockets, starting with a couple and ending with thousands to see how that affects performance, but I didn't do that in this video. Finding the right animation tool is always highly tied to what you want to show in the animation, and the only thing I need in this animation that isn't PNGs are dots, so that's the niche. Technical setup. Here's the code base. You can find it on GitHub. Basically, I have this code here that pre-generates all the planet and moon movements and stores it in these NumPy arrays. So each planet has things like XY coordinates, rotation and alphas through time, etc., etc. that I'm not going to go into in this video. So for this video, just assume that you have data structures with all the things you would want about where a planet is through time pre-generated, and now you want to use that data to render an animation using either Matplotlib or Pygame. Here is the main for Matplotlib, and here it is for Pygame, and they then use code from these two folders respectively. And as either of these front-end codes are run, an animation starts to render, and all the settings and whatever else one may be interested in is stored in this logger file. So here's how that looks. In total, I ran 48 experiments where each represents an animated video, and each result is stored as a row here. Here's the list of features in this logger, so the columns. Matplotlib versus Pygame, more specifically Matplotlib FuncAnimation versus Pygame 2.0. There is this artist animation alternative to FuncAnimation that I've never even tried, but from what I've heard, its performance is not supposed to be any better than FuncAnimation. Let's jump down to performance time. This is the target variable. And what this is how long it takes to generate 60 seconds worth of animation, and regardless of frames per second, so it is normalized. The lower it is, the better. And then I'll see how other features impact this perf time. So like resolution, the animation was rendered in either 1920, 1080 or 1280, 720 resolution. But note that the objects are always rendered in the same size in absolute pixels. So as you can see in 1280 resolution, the objects look larger, and this should also make the rendering a bit slower relatively for the 1280 case. But overall, I see this more as a detail than something that has a crucial effect on the results. You'll get what I mean when I get back to this in the results. Frames per second, 60, 100, or 144. For most experiments, it was set to 100. So I used two computers, a 10-year-old laptop that's worth maybe $200 today, no GPU, and a workstation worth about $700 that houses the NVIDIA RTX 3050 GPU. Both these computers are with Linux Ubuntu distribution, but that probably doesn't affect the results too much. Then there is this write parameter. It says whether the animation is shown live or written to an MP4 file. I wanted some way to estimate the compute load of the animation, so that's what these three features are. Number of PNGs, average diameter of the PNGs in pixels, and then the number of rocket dots. These two features are later combined in this compute load feature. so I can generate 2D plots from it. Then there is how much RAM is used and visual quality that I judge for some saved MP4s later, and number of frames rendered. That's used to see if there's any memory leak or slowdown when rendering longer videos. I'll also say a few words about the main dependencies used within Matplotlib and Pygame, because there may be more than one way to render these moving objects. In Matplotlib, the core library used for this is the transforms library, and it's a affine 2D function, which is pretty straightforward. Like for an image, first it's scaled, rotated here, and all one has to do in an animation is to say how much it should be scaled, rotated, etc. each frame. It's also possible to do this using OpenCV, but in a previous video I concluded that it's about 200 times slower to do that than using transforms affine 2D, so I didn't even try it here. In Pygame, the main function calls are these ones, so Pygame transforms smooth, scale, and rotate. I'll get back to this in the ease of use section later, but first let's do results. Let's start with visual quality between Matplotlib and Pygame. I'd say it's about the same. Matplotlib is better at preserving the original texture of the PNGs, whereas Pygame makes it a bit more granular looking. But main thing is that both suffer from this stutter problem. This is a zoom in on 1920 resolution. These planets stutter, and the slower they move, the more apparent it gets. I spent hours trying to figure out why this stutter happens and doing various complex workarounds to limit the problem. This is not a bug. First I thought I had some rounding error in my pre-generated data. This is how it's supposed to look. AI tells me that this should be caused by internal rounding or interpolation within Matplotlib and Pygame, because they can only work within the precision of 1 pixel. But to me this looks like it's a problem beyond 1 pixel, so I'm not really sure what's going on. The most valuable result is that Pygame needs about 10 times less compute time to render an animation. And as you can see, there's quite a bit of variation between the different compute loads. So the lowest ones correspond to this scenario, and these ones correspond to this. But it's super clear that Matplotlib is not even close when it comes to render speed. Resolution. Rendering an animation in 1280 resolution is about twice as fast as doing it in 1920. But resolution also has a big impact on visual quality, and it does help against the stutter problem. If we want to write the animation to an MP4 file, it's generally slower than just watching it live. For Matplotlib, it's always much slower to write the file, whereas for Pygame, it only gets slower for larger compute loads. It ends at about 25% slower. As expected, it's slower to run it on a $200 laptop than on a $700 workstation. As far as I can tell, this is because of both the GPU, but also because it has a better CPU. Also, these results show that it's much faster to run Pygame on a shitty laptop than Matplotlib on an OK workstation. Also, I did look for options to run Matplotlib with the GPU, but from what I've read, it's not really supposed to help, so I didn't. And similarly, I tried to disable the GPU on the workstation, but I couldn't figure out how to, and it seems like Pygame uses it by default. So here, for example, I commented out these lines that I thought were needed to run it with the GPU, and then ran the Pygame animation and checked in the terminal whether the GPU was still being used, and it was. So that's pretty neat. If you have a relatively modern system and a GPU, Pygame will use it by default. The following results are more like details. RAM, between 300 and 450 megabytes of memory was used when rendering. Matplotlib uses about 15% more than Pygame. Longer video equals slower performance per 60 seconds rendered animation. Maybe to some extent. The trends here aren't that strong, so there weren't enough experiments to draw any real conclusions. Frames per second. I mainly wanted to test this with regard to visual quality, whether increasing FPS helps against the stutter problem, and it doesn't seem to. For this type of animation, I would suggest to just do 60 FPS. However, take this result with a grain of salt, because as you can see, I didn't make the planet's velocities lower for higher FPS. So the planets there are moving faster, and the stutter problem gets more severe for slower movement, so it's not really a fair comparison. But I'm pretty certain that FPS has a much smaller impact on the stutter problem than, say, resolution. Finally, number of dots. So it's these ones flying around. The thing about them is that they're not PNGs, but rather rendered using plot in Matplotlib or as draw circle in Pygame. As I said before, they were not the main focus point for these experiments, but I did some basic regression analysis, and turns out these dots are only responsible for about 3% of the rendering time, and that corresponds with what we might expect. If you animate PNG images together with these types of dots, almost all compute time will be spent working on the PNG images. Ease of use. Overall, I think Matplotlib is slightly easier, but the difference is not that big. The only way to understand why is by diving into the code, so I'll do that now. I'm only going to focus on some main things, so don't try to understand every single line that I show. This is not a tutorial on the code, but more like some surgical strikes. It would take at least 30 minutes if I were to go through all the code. I'll start with Matplotlib, but as you'll see, a lot looks exactly the same in Pygame. So here's the main module for Matplotlib. We initialize the figure, and this x_b is a pointer to the canvas. These lines call the pre-generation of all the planets, moons, etc., their movements. This list D is the drawables, or list of artists. Basically, if you want to show something in the animation, like a planet, you have to put it in this list. It can also be a dict, but then blitting doesn't work, so list it is. Then in the animation loop, each of these planet objects, they're called O1 here, are looped over. If the animation frame I is the same as the object's start frame SS stands for start stop, then this start draw function is called. I'm not going to go through everything here. Basically, all these if-else's are because there are different types of sun system objects. This _s thing is shorthand for self. The line to pay attention to here is d_append xb imshow. This is where we load the pic, which is a PNG of a planet, for example, into D. And then later we want to modify it in this update draw. So that was start draw, and update draw is here. And here's where the Matplotlib M transforms affine 2D is called. To scale, rotate, and move the object, and to change alpha, so transparency, and Z order. These values are all pre-computed, as I said, and set according to this age parameter of the object, and that's how many frames since the object was generated. So after the object has been added to D, the next part here will kick in, and the age of the object will be incremented, and then update draw called again. When the object reaches its last frame that it should be showed, nothing is done here because the planets and moons are shown for the whole duration of this particular animation. But for the rockets, so the dots, they appear briefly and then disappear, and if they aren't removed, D would become really long, and that slows down the animation. So here I also have this remove draw function. These two sections should obviously have been combined, but basically what the remove draw does is remove the object from D, but then pointers of other objects in D will be messed up because D is a list. So then there is this decrement indices in D function that adjusts the pointers of all other objects in D after an object has been removed from it. This part is almost comically messy, and it's caused by the fact that D has to be a list. And it's also the messiest thing in Matplotlib Animations that I've ever implemented. In hindsight, it's also a hint that maybe the wrong tool is being used for this type of animation I'm trying to make here. But that having been said, if we scroll down, here is perhaps the nicest thing about Matplotlib, this call to FuncAnimation with all these parameters. You just don't have that in Pygame. Right, main pygame.py. If we scroll through it, on the surface it looks pretty similar to Matplotlib. We run an animation loop, and in each iteration we loop through all these objects and start draw and update draw them. There's no black box here, so in practice what that means is that you have to do some types of things more manually. So we go through the animation loop. First thing I noticed is that I cannot kill it using Ctrl+C, so I have to write this messy thing that kills it if I press escape. The next thing is blitting. In the Matplotlib code, all you know about blitting is that setting it to true makes it faster, but in Pygame you have to work with it more manually. Practically here, blitting means showing, and so think you have an empty screen, and what's the first thing I want to draw on it? It's the background picture. And then I'll draw more things on top of it, and the order in which they are drawn depends on their position in this list of drawables. So a big difference between Pygame and Matplotlib code is that here D is initialized in each animation iteration, whereas in Matplotlib you initialize it before the animation loop and then modify it. What that means also is that in Pygame you don't need this horrible code to remove objects from D when they're supposed to stop showing. You simply stop adding them to D. If I click Start Draw here, we see what it looks like for the Pygame case, and like in Matplotlib, we're going to add things to D, but instead of adding an imshow, here we're going to add a tuple with a pre-computed Z order, type, which isn't important to pay attention to, and the actual PNG, but now it's in this surf format. What is this surf? Let's click to surface, and basically it's Pygame's internal way of storing a PNG. Since my PNGs do use an alpha layer, there is this weird workaround that is needed for some reason. And then we have this rect, and that is, as far as I understood, only a way for Pygame to store the corner coordinates of any given picture. If we go back to main Pygame, we see that after objects have been added to D, it gets sorted here according to Z order and then blitted. So far, overall, this is about as complex as the Matplotlib code, but then we get to this thing down here. So if I want to write the animation to an MP4 video, I cannot just run this ani.save one-liner like in Matplotlib. No, I have to do this. So there is a whole extra module for it. So in each iteration, the surface image that's been rendered gets piped into an FFmpeg process. Sorting out this FFmpeg code is quite messy, and the syntax and the error messages are not that easy to understand. So all in all, I think Pygame is slightly more complex than Matplotlib Animation. So in conclusion, Pygame is the better choice for this type of animation with moving PNGs. And it's not because it's simpler or it produces videos that look better or because it works well with a GPU or because it gets some extra bonus for some resolution or FPS or when writing to an MP4. It's because it's 10 times faster in general than Matplotlib FuncAnimation. It's not even close. So why is that? I think there is more to it than simply stating that Matplotlib isn't designed for PNG animations. To me, this type of result is pretty typical of software that gives you this type of wrapper. You get this nice box that does stuff for you, so you don't have to worry about understanding blitting or any of these other parameters. But the cost is that there are these massive slowdowns when doing something just a little larger or outside the box. I'll end with this quote. Matplotlib gives you a high-level animation and rendering API where you don't need to know graphics fundamentals. It's intentionally mathematical plotting first, graphics second. Pygame, on the other hand, expects you to build the rendering yourself, and in exchange for that manual labor, you get performance and speed. But the manual labor really isn't that bad. Apart from the write module and some pretty straightforward stuff with a blitting list, the only other annoying thing is this messing around with the PNGs to make Pygame load them as surfaces. So a clear win for Pygame on this one. Thanks for listening.